In the first procedure, we must start by identifying the weight hanger we intend to have ascend, or go up, and the weight hanger we intend to have descend, or go down. In order for the Atwood machine to move, the ascending hanger must be lighter than the descending hanger. So we will begin by moving the descending hanger to be touching the foam pad on the floor, by pulling on the string that passes over the Atwood machine pulleys. Once we have added additional masses to the hanger, we will reverse this positioning to allow the Atwood machine to move on its own. Now we can add some additional mass to the weight hanger. First, we place two 50-gram slotted masses on the descending hanger, which is still located on the floor. The weight hanger should have a mass of about 50 grams, for a total approximate mass of 150 grams for this side of the Atwood machine, but we will confirm this later. On the other weight hanger, we will place a number of small masses, because we will eventually move some of these masses from the ascending hanger to the descending hanger to increase the mass difference. To create a mass system that is equal to the other hanger, we can add 10 of the 10-gram masses to this hanger for an approximate total mass of 150 grams as well. Notice that when the descending hanger is removed from the floor, that the system does not move. However, by adding one additional 10-gram mass to the descending weight hanger, the system will now accelerate on its own. Because we do not want to try and account for all of the error that each individual slotted mass must inherently contain, we will use the electronic balance to determine our system mass and individual mass values. This way, the error associated with these values will simply be based on the accuracy of the electronic balance, and will not have to be compounded by the number of individual slotted masses used. Remember that for this example, we placed 100 grams on each hanger, and that each hanger was approximately 50 grams, with one additional 10-gram mass placed on the descending hanger. This should make our system mass 310 grams, but the electronic balance indicates that we ended up 1 gram shy of this expected value, with only 309 grams. However, we do not need to compensate for this discrepancy. Rather, we will simply record these values as they are. Next, we will determine the mass of our lighter ascending hanger by weighing it alone. It would appear that our missing gram is somewhere in this stack of masses, which could make sense considering that many smaller errors would be compounded by the number of masses we used. But again, we will not worry too much about this. Swapping out the ascending weight hanger for the descending weight holder, we may determine the mass of the other hanger as well. Accurately knowing the mass difference between the two hangers, called delta M, is important for determining the accuracy of the Atwood system. So, to determine a delta M that would be much more precise than simply subtracting the two masses we just determined, we'll use yet another measuring tool called a pan balance. Notice that without any masses on the balance, that the needle at the center points to 0. A pan balance acts very similarly to a teeter-totter, where two masses are placed on either side of a pivot arm. If the masses weigh the same, the teeter-totter, or fulcrum, arm will remain parallel to the ground. Of course, if the masses are different, we would expect the heavier one to go down. We can demonstrate this by placing the heavier mass on the left side of the scale, and the lighter mass on the right side of the scale. Indeed, the heavier mass stays firmly seated on the ground. However, we can make use of a system of additional calibrated masses that most teeter-totters are not equipped with. By moving the sliders on the pan balance, we are effectively adding mass to the lighter side of the teeter-totter. Notice that by moving the smallest slider all the way to the right, the pan balance begins to move back towards the lighter mass, but the needle does not reach 0. This means that the mass difference must be slightly larger than 10 grams after all. Moving the slider back to 0, we can now move the larger slider up to 10 grams. Then we can slowly begin to move the smallest slider again. There is some subjectivity to this measuring device, but it appears that around 4 on the scale, that the needle on the balance reaches 0. What does this mean? Well, we know that the mass difference between the ascending and descending hangers must be 10 grams plus the 4 additional grams for 14 grams. Had we simply subtracted, we would have been missing approximately 3 grams of mass difference. After rehanging our weight hangers on the Atwood machine, we are ready to set up the GLX. First, we will plug in the digital adapter, and when prompted, select the linear smart pulley. We do not want the GLX to try and calculate acceleration for us, so we will set position and acceleration to not visible. Navigating to the graphing function, we will modify the data properties so that 4 digits are displayed on the plot. To perform our first data collection run, we now must winch the descending hanger up to its start position by moving the ascending hanger to the floor. Once the system is in place, we simply press the play button on the GLX and then release our masses. The heavier descending mass should begin to accelerate towards the ground, and a relatively linear line should begin to plot on the GLX. It may be a good idea to catch your ascending hanger before the descending hanger makes it to the ground, but however the system comes to rest, make sure to press the play button again to stop data collection. Pressing F1 on the GLX will cause the graph to rescale to better fit the screen. Using the arrow keys, we can now navigate along our data line. Since this is a velocity versus time graph, we know that the slope should represent the average acceleration of the system. To determine the slope, we will need 2 points from the line that are reasonably far apart from each other, but it is also important that both points reside on the linear portion of the line and are not taken from the bumpy parts that may be at the end or the beginning of the plot. The coordinates for the on-screen cursor can be found at the top, middle of the GLX screen. To complete this first procedure, we will conduct 3 additional drop tests with the same mass difference. In procedure B, we will simply move some additional small amount of mass from the ascending hanger to the descending hanger. For this example, we have made this process particularly convenient because the lighter hanger was composed entirely of small 10-gram masses. By moving 1 mass, we will increase our mass difference by 20 grams, because while the descending hanger is gaining 10 grams, the ascending hanger is losing 10 grams. We will complete 4 additional drop tests. Just as in the previous procedure, only each time we will transfer another 10 grams to the descending hanger.